Uh, so the topic for today is the other kind of special matrix, symmetric matrices, and particularly, dang it, symmetric positive definite matrices. But before getting to that, there's one more thing I want to do regarding banded matrices, and I'll do a little MATLAB demonstration involving them. Okay, so. All right. So what I'm going to do is I'm going to create a random matrix with lower bandwidth 1, upper bandwidth 2. All right. So first, I'll just create a random 5 by 5 matrix. I'm actually going to make sure that I format short. I don't need to see all the decimal places. Okay. Now, to make this a banded matrix, I can use functions that are normally used for creating upper or lower triangular matrices, tri-L and tri-U. So, so to make it have lower bandwidth 1, I want to remove everything below this first subdiagonal, and I can use tri-U for that. Now, this usage of tri-U, just one argument, would simply zero out the entire lower triangle to make the matrix upper triangular. I don't want to do that. So I will include a second argument of -1. So everything below the first superdiagonal, which is not given, subdiagonals are given negative numbers, will be zeroed out. So, well, first subdiagonal. Okay. All right. So here we have a main diagonal. Here's the first subdiagonal. Everything below is gone. And then I'll use the opposite function, tri-L. I want to keep the first two superdiagonals, zero everything above there. So tri-L normally creates a lower triangular matrix by zeroing out the entire upper triangle, but I don't want to go that far. Zero everything above second superdiagonal, which those are given positive value indices. Okay, so now I have a matrix that is lower bandwidth 1, upper bandwidth 2. So the next thing I'll do is form Gauss elimination with partial pivoting. As I mentioned, pivoting, so just Gauss elimination without pivoting will give a nice LU decomposition where L will have lower bandwidth 1 and U will have upper bandwidth 2, just like the original A. Pivoting messes with that. So go ahead and do some pivoting, and we'll see what kind of a mess we get. So can anyone tell me, if I'm going to start working from the first column and go from left to right, do I need to perform a row interchange to work on the first column? And if so, what kind of swap will I need to perform?
You need to switch 2 and 1, right? Row 1 and 2?
Yeah, I got to swap the first 2 rows because I need the largest element to sit on the diagonal. Currently it does not, so I need to swap the first 2 rows. Okay, so what I'll do is rows 1 and 2, all columns will be equal to rows 2 and 1, comma, all columns. That will perform the swap. And you see things are already messed up, we're already gone outside the band. Okay, and then I will perform a row operation to zero out this entry. So, so row 2 is equal to itself minus the multiplier, which is the entry I want to eliminate, divided by the diagonal entry in the same column, times row 1. So that will now the first column is done. Then I move to the second column, and we see again the row interchange is needed. The largest element is not on the diagonal. So I'm going to swap rows 2 and 3. Okay. And then I carry out the row operation to eliminate a 3, 2. All right, so row 3 is equal to itself. And then we have 3, 2 divided by 8, 2, 2. That multiplies row 2. Okay, so we're working our way towards upper triangularity. Okay, now we go to the next column. We again have to swap. This is terrible. Every possible pivoting that needed to be done, that may have to be done, does in fact have to be done. Okay, and then we'll just finish off this tedious process. We handle the third column. Eliminate a 4, 3. Okay, and then wait to the last column. Wow, this is a randomly generated example. It's still a call for pivoting every step of the way. So this is like a worst case scenario. Okay, so row 5 is equal to itself divided by minus a multiplier times row 4. Okay, so the matrix is now upper triangular. Now L, we can't see L here, we only see U. L does have a lower bandwidth of 1 because we only needed to eliminate one entry in each column. So that part was nice. But U, which would normally have an upper bandwidth of 2, can't really be considered a banded matrix at all. Because the entire upper triangle is filled, except for this one corner entry here. So loss of fill-in caused by partial pivoting. So here you get to see an example of just how much you can mess with things to have that happen. So, whoops. Any questions about what happened here, this once banded matrix? Okay. Now, we want to symmetric matrices. So to refresh your memory from whatever prior learning algebra course you had, a matrix is symmetric if it is equal to its own transpose. So symmetry is in respect to the main diagonal. So you see these two entries, the 2's match, 3's match, the 5's match. So Aij is equal to Aji throughout. Now, if we revisit the LU decomposition, and for a time being, we'll forget about pivoting. Now, in the LU decomposition, our factors LU are both triangular, but L is unit lower triangular, whereas U is just plain upper triangular. So L has a diagonal of 1, U does not. So suppose we try to write the LU decomposition a little differently, where I break U down into a product of a matrix D, which is diagonal, and then M transpose, where M is also unit lower triangular. So therefore M transpose is unit upper triangular. And the entries of D are just the diagonal entries of U. So it's pretty simple to obtain this decomposition. So in fact, here's a formula for M transpose. It would just be D inverse times U, assuming that all these diagonal entries are non-zero. Otherwise, we couldn't solve the system anyway. So now we have this factorization of A. So unit lower triangular times diagonal times unit upper triangular. And this is sometimes referred to as the Ltmt factorization. Try to notice when I'm supposed to be typing is too small to see. It happens now and then, and Now, this factorization is pretty useless until A is symmetric. So let's examine this factorization in the case where A is symmetric and see about the relationship between L and M. So if I take the transpose, then that would be MD L transpose. But because A is symmetric, that's equal to LD M transpose. So here, these factorizations are equal. Now, I can multiply on the left by M inverse transpose. Now, M is a unit lower triangular matrix, so it has an inverse. Because unit triangular matrices are always non-singular. And also, I can multiply on the left by M inverse. So now I have this relationship. So D times these matrices is equal to these matrices times D. Now, at this point, it may seem like I haven't really done anything. Like what I had is just as complex as before. But here's the key. So first, what's multiplying D on the right on one side is a transpose of what's multiplying D on the left on the right side. Furthermore, L and M are both unit lower triangular. M inverse is also unit lower triangular because inverting preserves triangularity and unitness. So, on the left side we have D times this unit lower triangular matrix transpose, and then the same unit lower triangular matrix over here times the diagonal matrix D. It's multiplied in the opposite order. But here we transpose. So here we have diagonal times unit upper triangular. Here we have unit lower triangular times diagonal. Therefore, the left side is upper triangular, the right side is lower triangular. The only way they can be equal is if both sides are diagonal. D is already diagonal, so that means that M inverse L has to be a diagonal matrix. But M and L are both unit lower triangular. The diagonal is all ones. So not only is this diagonal, it's identity. So M and L are equal. And now we have this factorization, A equals LDL transpose. So anytime you have a symmetric matrix, under similar existence criteria as applies for LU, we have this decomposition, which is often referred to as the LDLT factorization, where L is unit lower triangular. It's the same L as from the LU decomposition. D is diagonal, and then it's the same L as transpose over here. So now we solve AX equals B, and we have this factorization due to A being symmetric. It's similar to the process of working with LU decomposition. So you form forward substitution to solve Ly equals B. Here we have this diagonal matrix in the middle, so we're solving this diagonal system, but we've already seen how easy that is. You're just performing n divisions. And then you do back substitution with this unit lower triangular matrix to solve this. Now, the process seems so similar to solving AX equals B in a general case using the LU decomposition. So do we really gain anything? And actually, we gained a lot. It's just not obvious what you see here, but it's because these two factors are just transposes of one another, so they have the same entries, that the computational cost is half as much. So recall that Gauss elimination takes 2/3 n cubed, approximately 2/3 n cubed floating point operations. LDLT takes 1/3 n cubed. So you are saving half the work because of the symmetry. And if you have a symmetric matrix, you can always do LU on it, but you're not taking advantage of the symmetry at all. Therefore, you're incurring the full expense. But here you can save by doing it this way. So, questions so far about LDLT? Now, pivoting is still a problem. When you're dealing with a symmetric matrix, you don't want to just perform row interchanges like you would with partial pivoting because you'll destroy the symmetry. Therefore, what you should do is interchange rows and columns. So if you decide on a row swap for same kind of considerations as what motivates partial pivoting, okay, go ahead and do that. But then, once you decide on a row swap, you swap the same columns by multiplying on the right by the transpose of the same permutation matrix. And so that way because if A is symmetric, then PA, P transpose is also symmetric. So if you're in a situation where you might divide by 0 or have a really large multiplier, you go ahead and swap rows and columns and continue trying to compute the Ltmt factorization, and then still have the same savings. Now, a consequence of that is your solution X will therefore be permuted. So you have to take into account when you're solving the system. So solve. All right, so from AX equals B, all right, if I multiply by both sides by P on the left, and then I throw in a P transpose here, but then I have to put its inverse next to it. But P is an orthogonal matrix, so the inverse of P transpose is P. In other words, P transpose P is identity. So now you're solving this system. Okay. So the way you would accomplish that is if PAP transpose is LDLT, and you're solving LY equals PB, you're best familiar to us from the general case of Gauss elimination of pivoting. And you're still solving the same, so you have to scramble the right-hand side. And then you solve the same diagonal system as before. And then you perform back substitution. But the output is not your final solution W, but it's factor W, which is a scrambled version of your solution. So W is actually equal to P times X. Therefore, X is equal to P transpose W. So forward substitution, divisions, solve a diagonal system, back substitution, and then a permutation is all that's needed here. Because this vector Px, that is W. So W equals Px, X equals P transpose W. So this doesn't really take computations. There are no floating point operations involved. You're just rearranging the entries of W. So questions about the solution process when dealing with symmetric matrix and needing to pivot? Okay. Now, everything I discussed earlier was about general symmetric matrices. Now we're going to focus on a subclass, a very very important subclass of symmetric matrices called symmetric positive definite matrices. So if a matrix A is already known to be symmetric, then we say it is also positive definite, or abbreviation SPD, symmetric positive definite, if it satisfies this condition for any non-zero vector x, that this expression is always strictly positive. An alternative definition of a symmetric positive definite matrix is a symmetric matrix whose eigenvalues are all strictly positive. This is where I mentioned that to give a real symmetric matrix, the eigenvalues are real. And recall definition of eigenvalue and eigenvector. I just mentioned eigenvalues, that A times an eigenvector, which is non-zero, equals the eigenvalue times the eigenvector. So these eigenvalues, so A is n by n. A has n eigenvalues, which might repeat. And if A is symmetric positive definite, those eigenvalues are all positive real numbers. The determinant is a product of all the eigenvalues. And this function is handy now and then, but trace of a matrix is a sum of all the diagonal entries. That's the definition, but it also is equal to the sum of all the eigenvalues. These are good to know things related to eigenvalues. So since the eigenvalues are all positive when the matrix is SPD, and the determinant is the product of all the eigenvalues, then any SPD matrix has a positive determinant. We can also say that all the diagonal entries must be positive. And you can prove that by letting x equal to a column of identity. So if x is a column of identity, which is a standard basis vector, then this whole expression is a diagonal entry of A. And since this has to be positive for any non-zero x, then the diagonal entries must be positive, since that comes from this for specific choices of x. Also, whatever entry in A is the largest, it must sit on a diagonal. And because all the eigenvalues are positive, the determinant is positive, A is invertible, and the inverse is also symmetric positive definite. And I think I assigned that as one of the homework problems. It is one of the explorations in this section. I don't recall if I put it on the homework. I know I did it in 610. So, okay. I didn't check on what I assigned. Oh yeah, by the way, the homework 3 from 3.3, 3.4, I'm covering 3.4 on Monday. That assignment is up in Canvas, and we have hints also. So I just put that up today. Let's see, 1, 3, 4. If I look at what I assigned, yes, it is one of the problems I assigned to show that the inverse, if A is SPD, then the inverse is also SPD. And you're relying on this definition to show that. Now, checking if a matrix is SPD is generally not easy. There are certain cases where you can rule out a matrix being SPD. Like, for instance, if you see a negative diagonal entry, or if you see but the largest entry is not on the diagonal, that's a quick way to rule out being SPD. But the general case, if none of those apply, none of those telltale signs, to refresh your memory, we work with the principal minors of A, which are the determinants of the leading principal submatrices of A. So here, this is an example of, so this is a general leading principal submatrix of A that I call AK, and you're just taking the upper left K by K block. So it can be shown that, okay. Ah, yeah, okay. Like, where did I say it? So you extract the leading principal submatrices, you take your determinants, and those are the principal minors that are given here. So A is SPD if and only if all principal minors are strictly positive. We came across principal minors before because what I stated was that A has an LUD composition if and only if all the principal minors are non-zero. So what that means is, if you have a symmetric positive definite matrix and you want to use Gauss elimination on it, you never need to pivot. I mean, you might want to pivot because of you need to minimize round-off error, but it's never absolutely necessary. You will never be in a situation where Gauss elimination will break down due to having to divide by 0. So that's one nice thing about symmetric positive definite matrices, that you can, especially if it's banded, for instance, nobody can get away without pivoting, no pivoting. But that doesn't mean that the LU decomposition is the way to go. Like I mentioned earlier with a general symmetric matrix that is not necessarily positive definite, you would not want to do Gauss elimination in that case. So instead of using LU decomposition, you do LDLT because of symmetry. And you actually can use LDLT for the SPD case also and get the same savings. Another option is called the Cholesky Factorization. A is equal to G transpose, where G is lower triangular and has positive diagonal entries. So when it's symmetric positive definite, it has this factorization exists if and only if A is SPD. So the cost of computing a Cholesky factorization is same as LDLT, it's 1/3 n cubed, floating point operation. So again, half the cost of ordinary Gaussian elimination, again benefiting from the symmetry. And if you go ahead and compute this, then the way you solve Ax equals B is you perform forward substitution with G, and then which is lower triangular, and then back substitution of G transpose, which is upper triangular. So it's very much like the LU decomposition. You solve Ly equals B, and then Ux equals Y. It's the same idea. It's that the matrices involved are transposes of one another. So a Cholesky factorization algorithm, which I'll show you in a bit, only computes one of these factors because you know that the other one is this transpose, and that's where this cost savings comes from. It's worth mentioning that if A is SPD, so it has both of these factorizations, they're actually very closely related. So G is equal to L times D to the 1/2, which is just a diagonal matrix where you're taking the square roots of the diagonal entries of D, which should be positive. Actually, it can be proven that they're positive when A is SPD. So because these two factorizations are closely related, really, if you have one, you can compute the other very, very easily. And so it's called square root free Cholesky. And the reason for this is, as I'll show you, the algorithm for computing the Cholesky factorization requires taking a few square roots, or n square roots altogether for an n by n matrix. LDLT does not require square roots. I should also mention that some books express the Cholesky factorization differently. So instead of writing as GG transpose, where G is lower triangular, it's R transpose R, where R is upper triangular. But R is just G transpose. So it really is the same factorization, it's just written differently. There is a function in MATLAB that computes Cholesky for you. It's Chol. And Chol actually uses this form. So it actually returns the upper triangular factor. So a transpose of this factor G. Questions so far before I show you how you actually do Cholesky? example where I computed Cholesky factorization. So here's a symmetric positive definite matrix A. Now, a matrix that is symmetric positive definite does not necessarily have all positive entries. All the diagonal entries must be positive, but you are allowed to have negative entries off the diagonal. So what I do is I write A equal to GG transpose, where G is lower triangular, so that structure is included here. And you'll see that this factor is the transpose of this one. Like here I have G21, and here I also have G21 because this factor is transposed. So really what I need to do is compute all of these elements of G, the non-zero entries. And the way I can do that is I can work out the product of this matrix times this one, like get formulas for all the entries. And then I set them equal to the entries that I'm given of A. And then I can go through these entries column by column and solve for the entries of G. So if you go through them in the right order, you'll find like, oh, I can get a new entry of G each time I consider a new entry of A. So everything can be solved for. So if I start the process, I look at the 1-1 entry of this matrix equation. So if I compute the 1-1 entry of this matrix product, so I'm going across the first row and down the first column, all I'm going to get is G11 squared. That's what I have here. A11 is G11 squared. So I can just go ahead and solve that equation for G11. And so here we see we have a square root. And that's, but the diagonal entries are always positive. So we know we're going to be taking a square root of a positive number. Always choose a positive square root because G, the Cholesky factor, is required to have positive diagonal entries. So now I have G11. Now I'm going to keep going down this first column of this product. So like the 2-1 entry. So that I get from going across the second row and down the first column. But because of G being lower triangular, all I get is G21 times G11, and then I get nothing else. So here's my formula for A21. And I have G11 already, so now I can just rearrange this and solve for G21 just by dividing. And I can keep going all the way down through the first column. So I can get each sub-diagonal entry of our first column of G just by dividing the same entry of A by G11. So now the entire first column is filled in. Now I go to the second column. I start with the diagonal entry, G22. So the 2-2 entry comes from going across the second row, down the second column, multiplying corresponding entries and adding, and I get G21 squared plus G22 squared. But G21 I know. I got it up here. So I can use this to solve for G22. And I once again have to take a square root. And if I'm subtracting, as long as A really is symmetric positive definite, it can be guaranteed that this entry, this what's under a square root sign, will still be a positive number. In fact, trying to compute the Cholesky factorization is a good way of checking whether a matrix is SPD. If it is not, at some point the algorithm will fail. Either from computing the square root of a negative number, or maybe what's under here is 0, so this entry is okay, but then you're going to divide by it later, you divide by 0. So, so this algorithm will succeed if and only if A really is SPD. Now I have my 2-2 entry, and then I go down the second column, and here I have a formula for the 3-2 entry of a product, GG transpose. And I know everything in this formula except for G32, because these were computed from the first column. I have a diagonal entry already, I just don't have this. So I rearrange this equation and solve for G32. So again, dividing by diagonal entry, it just has to subtract something off first. So when I finish off the second column, going all the way down, then I get to the third column, I have a sum of squares. And these two entries are known because they come from a prior columns. So I solve for G33. I have one subdiagonal entry in the third column that I can now compute. Notice the expressions for these entries of A keep getting more complex. We're adding on more and more terms. But there's still always exactly one unknown entry of G, and we can just rearrange to solve for it. And finally get to a 4, entry, also a sum of squares. Everything, all these three are known, so I can rearrange this to solve for G44, and now all of G is filled in. So everything I did comes from the formula for matrix-matrix multiplication. That to get Aij, I'm working with row I of G and column J of G transpose. But now I express this in terms of the entries of G, and I have this formula. So by applying this formula to all the entries of A, at least the ones from the lower triangle, which is fine due to the symmetry, I can solve for all the entries here. So questions about this process of computing the Cholesky factor? Oh, what I'm going to do now is show you so that's a good way to compute the Cholesky factorization. For instance, if you have to do it by hand, like for a small matrix. Now, as far as I can show you another perspective, so this is the same example worked out in the text. Okay. But I'm showing another approach that if I let this equation here, Gj, refer to the jth column of the Cholesky factor, and I can express A as a sum of what are called outer products, because Gj is a column vector, and when you multiply a column vector times a row vector in that order, this product is a matrix. Whereas if I switched it, if I had Gj transpose Gj, row vector times column vector, that's an inner product, which is just a number. But the thing is, with G being G being lower triangular, G1 could have every entry non-zero, conceivably. G2 always has the first entry equal to 0. G3 always has the first two entries equal to 0, and so on. The consequence of that is that each one of these outer products has a smaller and smaller non-zero portion. So like G1 transpose could conceivably be a matrix that's entirely non-zero. G2 transpose, though, will have the first row and column 0. When J equals 3, first two rows and columns, all 0. That can be exploited to compute the entries of each of these vectors. So as a consequence of that, so this algorithm for Cholesky factorization is based on this outer product perspective. And you can see it kind of resembles Gauss elimination in a way, sort of, where we're computing this kind of reminiscent of the computation of a multiplier. This kind of looks like a row operation, but it's not really that. And we see three levels of loops. So it makes sense that this is an order n cubed algorithm, but still faster than half the cost of ordinary Gaussian elimination. So how this algorithm behaves is, like, first it computes the first entry of G1 to G11. Then it's computing the rest of G1, the first column of G. And then it's subtracting G1 transpose off from the rest of A. So then, after G1 is complete, we move to the second column, and we start doing the same process to compute G2. Subtract off G2 transpose. You keep whittling away at A until there's nothing left. So I'm looking at anything else here that in particular I want to point out. All right. Oh, okay. Now, I just want to show you, to talk about LDLT. Here's the algorithm for that. So it's even though it sort of came from Gauss elimination, but it's applying to symmetric matrix, there are significant differences in the algorithm for LDLT versus Gauss elimination, just because we want to make sure to compute L of D efficiently by exploiting the symmetry. So just tweaking Gauss elimination as little as possible isn't going to do that. So here we don't really have anything that corresponds to a row operation. And then again, that's for the sake of efficiency. All right. Okay. I want to point this out. This is from a problem that I did not assign. There's a very interesting property of the Ltmt factorization that each diagonal entry in the D matrix from the Ltmt factorization is a ratio of principal minors of A. And that can be used to prove, as actually carried out this problem, again, one I did not assign, that a matrix is SPD if and only if all of the principal minors are strictly positive. So the Ltmt factorization is very helpful for proving that existence criterion. Now, are there any questions about what we've seen here today, or anything ongoing with the homework? Everything's going swimmingly with homework? That is do today.
Dr. Lambers,
Yes.
would you mind opening the lecture notes from February 2nd?
Second. Okay.
At the top of page 2, I'm wondering about, number one, the relationship between P, L, and U, and all of the P's and M's up above it. And
Okay.
then a strategy for storing all of this during the process of Gaussian elimination with partial pivoting.
Okay. All right. So you want to see how do these factors relate to what's up here?
Yes, sir.
Okay. So, so P is a product of all the row interchanges that ended up being performed during Gauss elimination. In that order. So whatever happened when working on the first column, then the second column, and so forth. So if we're multiplying this order from right to left, then that's P. So yeah, so P is right here.
So the work that we did in the first bullet point on page 2 is showing how it is that all of those row interchanges were collected instead of distributed throughout. Because when we're actually working the process, we have a row interchange and then a type 3 operation. I'm struggling to think of the words here, so I'm just going to use type 1 and type 3 operations.
Yeah.
So we've got a type 1, then a type 3, then a type 1, then a type 3. So the 3 bullet points at the top, or the 3 lines at the top, are how it is that we rearranged so that all the type 3 operations are together and all the type 1 operations are together.
Yes. And now, so the thing is, yeah, whatever row interchanges are performed during the process, yeah, at least those can be gathered as is. Now, the type 3 operations are also subtracting a multiple of one row from another. Whatever you actually performed during Gaussian elimination is not exactly the same as what shows up in L. Now, so the multipliers do appear in L, just like in the case of Gaussian elimination without pivoting, but since what you're actually doing during Gaussian elimination is, M1, M2, all the way to here without the tilde. Because the matrix L, the answer to your first question, comes from taking all of these, inverting them, and then multiplying them in the opposite order from what you see here. So this matrix right here, this product is L inverse.
Okay.
And the thing is, okay, each of these M tildes has this definition in terms of the original operations that you actually performed. It's just that all subsequent row interchanges and also column interchanges have to be performed too. But as far as what happens in a practical implementation, really you're just doing this. So when you discover that you must do a row interchange, even though by that time, like say you're working on column J, and in your row echelon form, everything in the relevant rows to the left of column J is already 0. But you're also storing the multipliers in the lower triangle. So as long as you swap your stored multipliers, then even though this is what you actually did during Gauss elimination, the final result will consist of these, of the M tildes. And this swapping of your stored multipliers accomplishes that.
Okay, and then at the end we can just separate the L and the U out of the matrix that we stored.
Yeah.
like which is kind of why you had us do the one exploration, returning one matrix instead of two.
Yeah, and then now the other thing that has to be returned by when you have Gauss elimination with pivoting, okay, one matrix that stores L and U, and then you also have to, in some form, return as output P. But that's where, in the hints I recommended, the most economical way to represent P is as a vector of scrambled indices from 1 to n.
And then, if you don't mind, I have one more question. It's kind of a long shot.
Okay.
Off the top of your head, can you think of a reason why my U is correct until the last row, which is now all of a sudden a bunch of zeros and an infinite entry?
Oh, wait. Okay. So the last row is what's incorrect?
The last row of both L and U. Everything else is working. Right now, I've got a function that I'm trying to build that's just Gaussian elimination with the partial pivoting.
Okay.
So I'm just trying to return L, U, and P.
Yeah.
And for whatever reason, it's breaking down at the last row.
Huh.
Although that was with a 3x3. So actually, I don't know if it's the last row or if it's just once I get past the second row, everything's falling apart.
Yeah, it'd be interesting to see what happens if you try it with a larger matrix. I don't recall anyone having a problem like that before. Yeah, so off the top of my head, I'm not sure what we'll be causing that, but
Okay, I'll email you about it later.
okay.
Thanks a lot for the help on the.
Oh, sure. My hunch is it's something to do with how the swap is being carried out. But it's trying to think what could like introduce those zeros.
Thank you.
Yep. Other questions? Okay. So one more section of this chapter, and that's what I'll get into on